So chapter 5 is the last chapter of college algebra, and we're going to learn about a couple more functions, a couple more types of functions. Basically, to sum it up, we're going to learn about exponential functions, and by the way, that's kind of, I guess that's 5-1, and I don't know if I'll get to it today, but the inverse of exponential functions, their cousins, are the logarithm functions. So both of these are introduced in this chapter, the logarithm functions. But these logarithms come up in 5.2. So maybe I'll do that next class. We'll see how far we get today. So that's it. There are two more sort of categories of functions here, but they're related to each other. They're cousins. They're inverses of each other, is what they are. But let's start with one. So these exponential functions. Here's a classic. Okay, the classic exponential function is this. I did this when I was a kid. I went. There's this nice old lady in the neighborhood. You know, she was kind of rich, I think. So I went over there and I said, hey, I'll rake your lawn every day, you know, in the fall. I'll rake your lawn every day, but you got to pay me a penny the first day, and then 2 pennies this next day, and then 4 pennies the next day. And so I did that, and I told her we'll do it for 30 days. So I feel bad about it now. I really took advantage of this lady. She ended up broke, and I ended up rich. Sort of kidding. Maybe that's what. Anyway, so what happens? 1 penny. The next day, 2 pennies. The next day, 4 pennies. The next day, 8, 16, 32 cents. I worked all day for 32 cents. The next day, 64 cents. The next day, 128 cents, which, by the way, is $1.28. The next day, $2.56. The next day, $5.12. You ever done this? You probably did this when you were kids. $5.12. The next day, $10.24. You know, the next day, $20 and something. The next day, $40, $80, $160, $320. I'm losing track of the cents. And $640. Anyway, that's a classic exponential function. And I was kidding. The lady's fine, and I'm not really that rich. But I would have been. What was I doing there? Look at this again here. Let's do this again. So X was the days, and then Y was sort of my pay. She had to pay me every day. And I'm going to call the first day, day 0. So day 0, she paid me 1 penny. And then day 1, 2, 3, these are the days. And then she paid me 2 pennies, 4 pennies. What am I doing? Doubling it? By the way, I never used that word. Sorry, I'm doubling my pay is what I'm doing. 8 pennies, 16 pennies, 32 pennies, 64 pennies. Like I said, $1.28 or 128 cents. Or if you move the decimal over, it's $1.28, and so on. You know, it doesn't seem like I'm making a whole lot of money. You know, I worked all day for $1.28. I worked all day for 4 cents. But by the end of a month, I think I'm super rich. I don't know. What would help me, I don't really want to build this chart all the way to 30 days. I wish I had the equation for this. I know the equation for this. I wonder if you got any ideas. What is the equation for doubling your pay every day? This is a classic exponential function. I'd like to know the equation for this. Do you have any idea? If you looked ahead and read a little, maybe you'd have an idea. If you can just think. It's kind of hard for students to come up with this, though. I mean, you're doubling your pay every day. I can tell you, or I can sit here in silence and watch you suffer. I'm looking for the equation of doubling my pay every day. You might think, you know, oh, doubling your pay every day. Okay, 2 times X. Well, that doesn't work. On day 5, you would pay me 10 cents. On day 6, 12 cents. I mean, 14 cents. So 2 times x is not it. No, that's not it. That's a classic linear function, you know. 2 times x would just be adding 2 cents every day, I think. That's not really doubling your pay every day. No, it's not. Some people think maybe x squared. That's not right either. We've already studied parabolas, and that's not quite right. 3 squared would be 9. 4 squared is 16. 5 squared would be 25. 6 squared, that's not this. So squaring it, double. Do you know what it is? Have you thought of it yet? Well, so it's this brand new idea, and here it is. Well, I'll tell you what, maybe this will help. Let me help you with this. But it's called exponential function. Check this out. You know, on day 1 here, this 2 could be thought of as 2 to the first. And then on the next day, what did we do to this 2? We doubled it. We multiplied by another 2. Well, if I multiplied by another 2, it got me to 4, of course. But if I multiplied this by another 2, you could think of it as 2 squared. And then if you multiply him by another 2, you could think of this as 2 cubed. And then the next day you multiply by another 2, and so here it is, it's 16, but you could think of it as 2 to the 4th. And this is multiplying by another 2, which would be 2 to the 5th, and so on. By the way, on day 0, you could call this 2 to the 0. Anything to the 0 power is a 1. That's one of our exponential rules. So now do you know what this equation is? You see the pattern? Day 1, 2 to the 1th. Day 2, 2 squared. Day 3, 2 cubed. I think the pattern is 2 to the x. And that's new and different. I mean, this is a new category of functions. I mean, we've dealt with x as the base. X has been the base. We've put different exponents on it. But now what we have is a base that's a number, and the exponent is the variable. That's new. That's new. The base is the number, the exponent is the variable, and that makes us fall into this category of exponential functions. And this is classic, double your pay every day. This is it. This is it. Day 7, plug in a 7, you get 2 to the 7th. Calculator would help you, but that's 128 cents. That's 2 to the 7th. Now, you want to figure out how much I made on day 30, the last day of our contract? The poor old lady, she barely had any food left to eat. She came out and she had to pay me 2 to the 30th pennies. You need a calculator for this. By the way, we need a calculator in Chapter 5 quite a bit, and we need to learn how to use it. We need to know how to find our exponential button and use, and if you do 2 to the 30th, your calculator might start smoking. I'm just kidding. What is 2 to the 30th? Anybody got an answer? This is how much she had to pay me. Holy crap. On day 30th, poor old lady had to pay me that many pennies. 107.37, 418, that's what I got. 2.4. That many pennies, let's turn it into dollars. To turn it into dollars, I'll move the decimal over 2 places. It's a dollar, right? Is that okay with you? It's this many pennies, but if I move the decimal right here, it is, holy mackerel, for raking all day on day 30th, I got $10,737,418.24. For some reason, she didn't want me to come back the next day. I couldn't figure that out. Would have been $20 million. Cool, huh? Exponential functions. Let's look at this guy again. Same function. So this is the reality of me and my neighbor lady. Okay, real function, except I'm kidding. If I forget about real life and money and taking advantage of people, then let's just do math. And if I think of this function doing math, let me plot what happens when you get some negative exponents. What if you do -2, -1? Let me plot these points. What happens when you plug in a negative 2? You guys know what 2 to the negative 2 is?
1/4.
Good. So we have to remember about a little bit of stuff about exponents. By the way, the Chapter 5 toolbox has some exponent stuff, and I might need to talk about that before we quit today. But we've alluded to this occasionally here during this semester, reminding us about exponents. This is stuff you should know from previous classes, but I'll remind you some more. He just said it though. What did he say? This is 1/2 squared. That's how you handle a negative exponent. It puts it into the denominator and makes it positive, which is a 1/4. What about 2 to the negative 1? 1/2 to the first, which is just 1/2. What about 2 to the 0? Plug a 0 into it. It's this function, by the way. Plug a 0 in, you get 1. Plug a 1 in, you get 2. Plug a 2 in, you get 4. You guys with me? Okay. I want to graph this little picture, which is kind of this picture, except I wanted to plot a few negative numbers, and I really can't plot all these points. It gets too high too quick. But let's just plot these points here. Negative 2, well, hang on. At 0, we get this y-intercept of 1. I guess that's my y-intercept. At negative 1, it's a half. At negative 2, it's a fourth. And at 1, it was a 2. And at 2, it was a 4. By the way, what is it at 3? Can you tell me what it is at 3? Plug in a 3 and you get 8. You know what's kind of cool? I can see this doubling. Can you see this doubling every time? The y values are doubling. What was the y value here? 1/4. What happened? It doubled to 1/2. What happened? It doubled to 1. What happened? It doubled to 2. It doubled to 4. And you create this graph. It starts off slow, but then it really, it's steep. It's steeper than any graph we've discussed. We've done parabolas, we've done some cubic functions, they're pretty steep. This is steeper than anything. It gets, the y values increase quite rapidly. The y values increase quite rapidly. I mean, when you look at this, it maybe feel like it's slow at first, but it increases quite rapidly. If I go out here to 30 and try to plot this point 30, it's $10 million. It's actually, you know, move the decimal back over if you actually want to plot it. It's a billion pennies. So this is it. This is a classic, this is y equals 2 to the x power. The x is in the exponent, the variable is in the exponent, the base is a number, 2. And it's a classic exponential function, and this shape is classic exponential growth, we call it. Exponential growth. Because it is increasing. This function is increasing drastically, exponentially. I mean, we use that phrase in society, you know, oh dude, it's increasing exponentially. Well, this is what it really might mean. And what that really means, okay, is that you're multiplying all the y values by some number every time. You're multiplying by some number every time. When you draw this, you know, good old exponential growth, steep as hell, getting high as hell. Listen, when you head toward the negative direction here, it gets very small. That was a 1/4. Then next is a 1/8, then a 1/16. It's very small, but it will never hit 0. So this x-axis acts like an asymptote, the horizontal asymptote. I'm not using really, I'm not reverting to any horizontal asymptote rules. There's an asymptote here, a horizontal asymptote that the graph approaches and never crosses, never touches. Because it never gets to 0. The mathematics won't let it. It gets small. When x is negative, it gets very small, but not negative, not 0. Let's do another one. Let's do another one. Let's do another one. And maybe let's put this into a word problem. Let's look at this. Let's do. I bought a new car for $25,000. It depreciates. It loses value as soon as you buy it. It depreciates. It loses value. It loses 20% every year. Okay? Maybe I should have waited. Maybe I should have done a few more examples, but this is good. This is good. This will get a point across, I hope. You guys, how do you calculate a 20% discount off of something? And that ain't the word. The discounting what's going on here, sorry. But I'm losing 20% of this value. How do I calculate a 20% decrease? What do I do? Multiply it by 20%, find out what that 20% is, and then subtract it from it. Does that make sense? Right, find out what the 20% is and subtract it from it. Watch this. If you take $25,000 and multiply it by 20%, sorry, multiply it by 20%, and then what did we say? Subtract it from it. Subtract it from the original 25,000, right? Is that what we're saying? I want you to see something here. I want you to see this. Factor out the 25,000, which might feel weird to you, but what are you left with right here if you factor out the 25,000? Factoring out 25,000 leaves me with a 1. Is that okay with you? Factoring out 25,000 over there leaves me with 0.20. Is that okay with you? What's 1 minus 0.20? 0.80. I don't know if you ever thought like this before, but here's what I'm trying to prove to you and suggest to you. When you take 20% off of something, you can take 20% of it and subtract it from it. That's logical, and that's what we all decided to do. But another way to do it is, if you're taking 20% off of something, then what the value that remains is 80% of what it was. So instead of taking 20% off, you could just multiply by 80%. That's what I sort of just tried to prove to you here. Taking 20% off is multiplying by 80%. So then that's how I want to think of this. I'm taking 20% off every year, but what I'm doing, the way I want to do that is I want to multiply by 0.80 that first year. Hey, what's going to happen the next year? It's going to lose 20% again. Does it say every year? It loses 20% every year. So the first year I'm going to multiply by 0.80 to see what the value of the car is. It lost a lot of value. Anyway, what do I do the next year? Multiply by 0.80 again, lose another 20%. What do I do the next year? Multiply by 0.80 again. What do I do the next year? Multiply by 0.80 again. This is what an exponential function is. It's new to us. When you multiply by something every time, that's an exponential function. And that thing you multiply by is the base. That's what this was. I multiply by 2 every time. I multiply the y values by 2 every time. That's an exponential function base 2. What I'm suggesting here is I have an exponential function that starts at 25,000, but what do I multiply by every time? 0.80. And so I'm going to write this as 0.80 to the x. This is the equation for this. I hope I convinced you. This is the equation for this little word problem. And if I want to know the value of my truck in 15 years, or my car, my new car, I got a formula here. Did I convince you? Taking 20% off every year is multiplying by 0.80 every year, multiplying by a number, multiplying by the same number is what an exponential function is. That's what I'm multiplying by a 2 every year. I'm multiplying by a 0.80 every year. The first year it's 0.80 to the first. Then it's 0.80 to the second. Then it's 0.80 to the third. It's how it works. So how much is my truck worth in 15 years? In 15 years, X is 15. I need a calculator. I need 25,000 times 0.80 to the 15. Yeah, good luck. You need a calculator and you need to learn how to use it. What we really need here is an exponential button. Listen, you guys, I'll try to help you. Sometimes it's 0.80 and you use this little caret symbol to the 15. It depends on your calculator, but that's one way to do an exponent. It's important to identify what's the base. What is the base on this problem?
25,000.
No, the base is the base of the exponent. The exponent's the variable x. The base is the 0.80. The 25,000 is not part of the base. That was sort of my point here. The 25,000 is waiting out front. So you have to do the 0.80 to the 15, then multiply by the 25,000. I was trying to help you use your calculator. Maybe you got this kind of an exponent button. Maybe you have this kind of an exponent button. You do this, there's this y to the x button, where so you hit the 0.80, you hit the button, then you hit 15, and then you hit equals. You with me? I think that's how it depends on your calculator and what kind of buttons you have, but you should learn how to use them. Anyway, when you get this answer, please multiply by 25,000. Can you tell me the final answer? What'd you say?
879.60.
Good. If these are dollars and cents, if we're dealing with dollars, then let's get in the habit of rounding to 2 decimal places for dollars and cents. So you just said 0.60. Thank you. So that's it, huh? $879? Yeah. 15 years? It's kind of scary, but that's about right, I guess. If it's still running. That's what it's worth. What a ripoff. Yeah, a classic example of an exponential function. If we drew a picture of this one, if we drew a graph of this one, I tried to convince you a lot of things here, but watch this. This is real easy. In year 0, how much was this thing worth?
25,000.
Thank you very much. That's this point. That's the Y-intercept. If you can do it like this, plug in a 0, and what do you get? You get 1. Anything to the 0 is a 1 times 25,000. All right. Then after year 1, you lost 20%. So I don't know where you are. You're 80% of where you used to be. Anyway, after year 15, we're down to $879. So this is not exponential growth. This is an example of reverse. This is exponential decay. It's this curve. It heads toward, it will never be worth 0 or less than 0. It heads towards an asymptote here. When you keep losing 20%, you'll never get negative. You'll never get to 0. So there's an asymptote that it approaches, and it's this shape curve, and it's high as hell over here, but that's kind of irrelevant over here in this word problem. In this word problem, it all started right here. Drastic, maybe it should be a little more kind of drastic drop at first and tapers on off here a little bit. Maybe that's a little better look. But this is exponential. We refer to this as exponential decay. And that's it. There's not thousands of different kinds of exponential functions. There's either this. There's 2 kinds. There's exponential growth or exponential decay. What does it depend on? What does it seem to depend on?
Whether or not the base is less than 1.
Good. The base. The base is the thing you multiply by every time. This is very logical, but if you're multiplying by a number bigger than 1, dude, it's going to grow. If you're multiplying by a number less than 1, dude, you're going to decay. Right, good. It's very logical. The base is what you multiply by every time. And so it's either bigger than 1 or less than 1 is kind of how we can determine growth or decay. Growth or decay. Here's another way, actually. Check this guy out. All right. Here is an exponential function. I mean, you know, how do you know? How do you see when you recognize, when you just visually see it? How do you know it's an exponential function? The variable is up in the exponent. The variable is up in the exponent. It's an exponential function. You know, you guys are smart. So what did we just say a minute ago? We said, oh, if the base is bigger than 1, it's probably growth. If the base is less than 1, it's probably decay. Well, here's a different way of thinking. This is a base that's bigger than 1. The base is 3. But with that negative x on it, it's going to decay. This is another way to decay. Having a negative sign on that variable makes it decay. How can you think about that? One way to think about that is like this. Look at this, classic 2 to the x. You know, if you stuck it, instead of an x, if you stuck a negative sign in that x, do you remember about our reflections and everything? Do you remember how that would flip it? A negative sign on the x flips it sideways. I didn't test y'all too hard on that, flipping sideways. In fact, I might not have tested y'all at all on flipping sideways. But a negative sign on the x flips it sideways. If you flip this sideways, it's exponential decay. The other thing is just to plot some points and watch it decay. I want to plot some points here for just a second here. Watch this. I want to plot a few points. Just a few. What happens if you plug in a negative 1? A negative 1 gets plugged in, turns into a positive 1, of course, and you have 16 times 3, which is 48. Did you follow that? Plug in a negative 1, it's a positive 1. 3 to the 1th is a 3 times 16 is 48. Plug in a 0. When you plug in a 0, 3 to the 0 is 1. Anything to the 0 is 1 times 16 is 16. Plug in a 1. When you plug in a 1, it's negative 1. Okay, so it's 16 times 3 to the negative 1. 3 to the negative 1 is 1/3 times 16, so this is 16 thirds, or your calculator would tell you 5.333. All right, that's enough for me. I got this figured out. Yeah, I can see it. Look, I can see it decreasing. As x increases, this is decreasing. This is classic exponential decay. I could plot the points and graph the curve. You know, you can use your calculator. I'm asking, you know, I want you to understand exponents, but your calculator will help you. 3 to the negative 1, if you can figure out how to type it in, times the 16. You gotta, it's important to don't put the 16 in there as part of the base, okay? The 16 is waiting out front. Anyway, where am I here? Negative 1 was a 48, way to hell up there. 0 was 16. And 1 was 16 thirds. 5 1/3. Yeah, I think I got classic exponential decay here. And now look, it's going to taper off toward the x-axis though. It bends toward the x-axis, never crossing, never touching, acting like an asymptote there. You guys okay? Okay, good stuff. So let me try to summarize something here. So, so in general, now I'm going to talk a little more abstractly here. I'm dealing with these kind of functions then. A times b raised to the x. Now, when you have these kind of functions, we're learning a few things. I'll tell you one thing though. Do me a favor and plug in a 0. When you plug in a 0, what do you get? Doesn't matter, look, doesn't matter what the A and the B are. You plug in a 0 for x. B to the 0 is a 1. 1 times A is A. So you always get this A. And now wait a minute, I'm plugging in a 0 for x and I'm getting A. This is my famous Y-intercept. So this is always your Y-intercept. It's always this number in front of the base. I mean, you don't have to memorize that. You just plug in a 0. You can get your Y-intercept if you plug in a 0. But it is that number in front of the base. It was on this, wasn't it? Look, wasn't it 16? This one was a 1. The number in front of the base, I guess, was a 1. Remember my new truck, my new car, the Y-intercept was 25,000. That's where it started. So cool. The Y-intercept is this number in front of the base. And then what did we say? We said if the base is bigger than 1, it's exponential growth. If the base is less than 1, it's exponential decay. This is good notes. This sort of summarizes everything here, except for one other little thing. There's another way to decay. What's the other way to decay?
Negative exponent.
Right. So if you have a negative exponent and the base is bigger than 1, so b is greater than 1, then this is decay. Sorry. This is exponential decay because of that negative sign. So these are pretty good notes. I got this function that's either growth or decay. Then I get this other option. I got this other way to decay.
So if the base was less than 1 and it was a negative exponent, would it grow?
It would. And I hate to, I mean, that's logical, and maybe I should put that up there, except, I don't know, why would we do that to you? I mean, we got a good way to grow. We got a good old positive exponent with a base bigger than 1 is growth. But you're saying you discovered another way to growth. Right. A base less than 1, but a negative exponent. You're right. Yes. That would be growth. I mean, that's logical, and you're right. But I don't even want to write it down. I feel like we don't do that. When it's growth, we do it one way. When it's decay, we got a couple ways. Right. You guys follow that? Cool. All right. You know, the other subtle little thing, let's put this in our notes. That base, that B is the base, you know. It could be, one way to think about that base, it depends on the problem. Sometimes I just give you, you know, the base is 3, you know. Sometimes you're just given the equation or whatever. But when I did that little word problem about losing 20%, sometimes it's cool to think of the base as being either 1 minus R or 1 plus R, where R is the rate of growth, where R is the percent, is the rate. The growth rate or decay rate. R is let me say that, I'm sorry. Where R is the growth rate or decay rate. See, again, one more time here. I said my car was losing 20% value. So the rate was 20%. Was that a growth rate or a decay rate? Well, I said losing value. So it was a decay rate of 20%. And what did I do with the decay rate? I subtracted it from 1. You know, if something's growing at 20%, you could, you know, the logic is, you would multiply by 20% and then add it to it. But you could just multiply by, if something's growing at 20%, you could multiply by 1.2. Right? In fact, maybe I should, my note, hang on, I got better. This R is a decay rate because you're subtracting it from 1. This R is a growth rate because you're adding it to 1. Maybe that's better. It depends. It depends. I don't know if you need this, but this is how you can create a base. If you have a rate of growth or a rate of decay that you want to add or subtract to 1, you can create this base. Is that? I mean, you know, I did a lot of math all my life before I came up with this idea. You know, I mean, when somebody said, "Oh, we're gonna add 15% every time. Every year we're gonna add 15% to your salary." Oh, great! But I would have to take my salary, and I'd have to multiply by 15% and then add it to the previous salary, right? I mean, that's what I would do. Multiply by the 15%, then add it to the previous salary. What I've just tried to teach you today, though, is that instead of the two-step process, you can instead take your salary and multiply by 1.15. That's how you can get to the new salary level. Same with losing 15%. If you're losing 15%, you can multiply it by it and then subtract it from it. Or you can just lose 15% by multiplying by 85%. Again, maybe you're experts at those ideas, but maybe not. Maybe, I mean, like I said, I did a lot of math before I ever thought about that. But it makes a lot of sense, and it saves a little time. And it applies to these problems, I think. Sometimes, in the word problems. So you've seen me mess around here today with some different bases. I started with a 2. Over here a few minutes ago I had a 3. And I had a 0.80. You know, I've had a few different bases. So you can have any kind of base. Here's just another one for fun here. 13 times 4 to the x. I mean, real quick, you guys, growth or decay? Growth. He says growth. How does he know it's growth? The base is bigger than 1. And it's a positive variable x, right? So growth. So this is classic growth. And then you've seen me plotting points. Listen, but I'm sick of plotting millions of points. Can you please identify, I want to plot 1 point. I want to plug in a 0 and get the y-intercept. If you plug in a 0 and get the y-intercept, what is it? It's easy.
13.
It's 13. Because when you plug in a 0, it's 4 to the 0, which is a 1. 1 times 30, you get 13. So that 13 is the y-intercept. It is growth. You know what? That's all I need to know. There it is. Here's a classic, beautiful picture of it. I mean, I could try to be more accurate and plot more points. But roughly, if it's exponential growth, it's this shape. If it's exponential decay, it's this shape. You know? That's it. There's an asymptote here to remember. Try to remember that. I don't want you drawing. I don't want you crossing this. You need to kind of approach this. But you get the y-intercept, and you know it's growth. You draw it. You don't have to plot a bunch of points. You know, this 4 to the x is a little steeper than my 2 to the x. That's true. It's a little steeper than my 2 to the x that I had earlier. All right, well then, guess what? These are all, so that's a base 4, base 2, base, all these different bases. These are all exponential functions. Listen, there's one special guy called the exponential function. And the exponential function happens when your base is this number e. E to the x. E is a number. You know, you may not have heard of it before. It's a famous number in nature, like pi. You've heard of pi. 3.14, blah, 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 blah. The irrational number comes out of nature, comes out of the measurement of a circle. So does the number e. It's not really geometrical like that, but this number e is 2.71828, dot, 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 dot. It's another one of these irrational numbers, like pi. It's a famous number that comes up in these exponential functions. We use it as a base for an exponential function, and we call it e. So maybe this is your first time learning about this number. Maybe you've heard of it before, but we use it a lot in chapter 5 here. We got to find there's a button on my calculator probably. There's an e to the x button on my calculator that I need to be able to use. But we write it e. We don't call it 2.7, but that's roughly what it is in your head. In my head, sometimes I pretend it's a 3, which means I'm rounding it quite a bit, but roughly it's a 2 or a 3, and it's your base. And so this is good old exponential growth. If you plotted a point, plug a 0 in. What's e to the 0?
1.
Yes, anything to the 0 is a 1. So it's good old exponential growth. Here's a picture of it. Y equals e to the x. And like I said, all these things are exponential functions, but we call him the exponential function. E to the x. Could you quickly graph this? Could you quickly graph this? 4,320 e to the negative 0.12x. Now look, so I just taught you about this e to the x, very basic exponential function. Now I went over here and got real complicated on you, but did I? How complicated is this stuff, you guys? It isn't that complicated. Listen to me. Let's start with the y-intercept, please. How do you find the y-intercept, or what is the y-intercept? You know.
It's going to be 4,320.
Yes, if you plug in a 0, you get e to the 0, you get this number. So yes, the y-intercept is this number. So 4,320. Now let me ask you something. Here I go. Is it growth or is it decay? Well, the base is bigger than 1. It's an e, which is bigger than 1, 2.7. And it's got a negative sign. Now, it's got some other little numbers multiplied by the x, but the main thing is it's got that negative sign, which means it's decay. So it's decay. So how do you decay from... Again, plotting some more points might get something a little more accurate, but I swear to God, that's the shape. This is good enough. You got a y-intercept labeled for me? You following me? It's easy. Looks scary, new, and weird, but it's not. This chapter 5 might be a lot of new information that you haven't seen before. I mean, when you came into this class, you probably knew a little bit about slopes and lines, you know, and you knew a little bit about parabolas. I mean, some of this class has been a review of some high school algebra and stuff like that. This might be new. Maybe not. Depends on where you've been in your career. So it's new and different, but it may not be that hard. It may not be that hard. You have to practice it and see what you've been. We use this, again, things in life do grow like this, you know, like cars and trucks, and they do depreciate exponentially. They usually don't depreciate linearly. I think 2 months ago, I did a truck depreciating linearly. Anyway, I think this is more realistic here now in chapter 5. Stuff depreciates more exponentially. Populations grow exponentially. Populations grow exponentially. Radioactive substances decay exponentially. Money that earns interest, and the interest is compounded, money earning interest grows exponentially. So there's a lot of good applications of exponential functions. Stuff in nature, in the world, grows and decays exponentially. Let me see something. Let me just check something. This book organizes things just a little different than I do sometimes. I want to double check something here. Give us this right away. Yeah, right away they start to use some. They start to right. They do this. Let's do this real quick here. If you have an investment and the interest is compounded continuously. See, in the past I've lectured on these ideas, but I've organized it a little differently. So we're earning interest. You know, you put money in the bank and in a savings account, the bank should pay you some interest. They don't pay you much interest nowadays. Interest rates are real low. They don't pay you much interest. If you put your money in the stock market or in some mutual funds, it should earn interest. It should grow. It should grow at a certain interest rate. If you leave that interest in there, the interest itself earns interest. That's what compounding interest is. You put your money in the bank, it earns interest, leave it in there, and your interest earns interest. And that's compounding interest. And if it's compounded continuously, you have this formula. Do they call it A? Is that what they do here in this book? Nah, they call it. Yeah, they call it S. Equals P e to the RT. So, I don't know, in other books I've called this A. Either way, this is called Y, if you don't mind. This is Y. And what is it? This is the final amount of money. The final amount of money. I guess that's what I'm calling this S. They called it S in our book. It's the final amount of money. Do you know what P would be? By the way, look where it sits. It sits in front of the base. What is P? What is P? What is this P? It's the Y-intercept. It's the original amount of money. It's the original amount of money. It's called P because we refer to that as principal. The original amount of money, the principal. The principal. The little r is the interest rate. And I guess it should be a yearly interest rate if we measure time in years. So T would be the time, and it would be in years. If this is a yearly interest rate, then this should be in years. And you can watch your money grow with this formula. Let's just try it. Let's just say I had, let's say I had $10,000. Let's just pretend I had $10,000. I put it in the bank. It earns 8.4% interest. And they need to use the phrase compounded continuously in order to use that formula. Compounded continuously, which I haven't explained too well, but that lets me use this formula. Okay, so what's the question? I put $10,000 in, I earn this interest rate, compounded continuously. The question is, how much money will I have? How much will I have in 30 years? I should just leave it in there, dude. I shouldn't touch it. How much will I have in 30 years? So it's just a little formula. Let's try it. You ready? S is the future amount of money. Sometimes they call it the future amount. I call it the final amount. The future value, sometimes they call it. The future value. So here, that's what I want to know. The future value of my money, S, which is the principal. What's the original principal? That's the $10,000 I put in the bank. E is the base, and it's raised to, what's it raised to? The R times T. The R is the interest rate. Hey, you got to write your interest rate. It's given as a percentage, but you should write it as a decimal. How do you write that as a decimal?
0.084.
Yes, 0.084. Is that right, you guys? You moved it over twice? Yes. 0.084 times the number of years. 30 years. Wow, okay. 30 years times that interest rate. E that. That means you got to find your E button. I never did ask you to find your E button. Can you find your E button? Can you do E to the first? What's E to the first? I'm sorry, I'm backing up. I'm sorry, I jumped around a little bit. E to the first, can you find that on your button, on your calculator?
2.718281828.
Yeah, good. There actually is no pattern. It feels like it for a minute there. There is that 1828, 1828, but then there's really no pattern. But anyway, cool. That's what I told you E was. You can do E squared. You can do anything. What I need is, what do I need? I need E to the 0.084 times 30. What is 0.084 times 30? 2.52. I need E to the 2.52. That's what this is. And then after I get that, then I multiply by the 10,000. Sort of depends on how your calculator works. But now I'm going to find my E button. It depends on how your calculator works. I got a button called E to the X. When I hit my E to the X button, it's waiting for me to type in an exponent, 2.52. Hit enter. Wow, cool. When I did this, I got 12.4285. Is that what you got? I don't know, you guys might be way ahead of me. Then I multiply that by the 10,000. So the final answer is, damn, 124,285.97. Again, this is money. Let's round it to the dollars and cents. How you guys doing? Were you able to pick up your calculator and find that number? Cool. Good job. Yeah, if you got 10,000 sitting around, put it in. You can't earn 8.4% interest at a bank, but if you put it in the stock market and well-balanced mutual funds, maybe you can get that for 30 years. It will turn into this. You know, the problem is in 30 years, see, there's another little thing going on in society, and it's called inflation. So like today, $124,000 sounds like a lot of money. In 30 years, $124,000 might buy you a cup of coffee or something. No, inflation's not that bad. But $100,000 in 30 years ain't what $100,000 is now. Inflation kind of eats away at it. Its value isn't what it was. But still, it's better. So there's a lot going on. But I'm done today. That was a good introduction to exponential functions. You can try some homework. You can try messing with the toolbox a little bit, and I'll help you.